Hello everybody. This is the project video by Group 17, and we'll be providing an in-depth presentation of our approach and methodology for our project in the Kaggle competition. The following is the overview of our presentation. We chose the cassava leaf disease classification challenge on Kaggle. It involves coming up with a solution to classify images of cassava leaves according to the categories of diseases they may have. Before delving into the details, let's highlight the performance of our top-performing model. Our model achieved a public score of 0.8980 on the test dataset in Kaggle, showcasing its effectiveness in accurately classifying cassava leaf diseases. Our model is also expected to rank among the top 35.1% of the Kaggle submissions. We begin by performing exploratory data analysis, EDA. During our exploratory data analysis, we see that the provided trained dataset has over 21,000 leaf images, and the test dataset has one RGB image. The majority class, the CMD category, contains 13,158 images, while the CBB category is the smallest of the minority classes, with 1087 images only. Inspection of the train and test datasets reveal that all of the images provided come in an 800 by 600 dimension size, and there is no standard procedure to how they are taken. For example, certain images are taken in conditions such as different lighting or zoom levels. Images of leaves may also be in the palms of a person, or maybe a small section of a wider field, constituting background noise. The analysis highlights several challenges in the dataset: visual variability, background noise, and class imbalance. These factors prevent immediate use of the training dataset. Therefore, it's essential to perform data pre-processing before proceeding further. Now, we perform data pre-processing on our training dataset. Techniques such as normalization and data augmentation were used. Normalization of image pixel values to 0,1 helps to prevent large magnitude features from affecting the training. It also ensures stable convergence of the model. Data/image augmentation is the process of applying various transformations, such as scaling, flipping, rotation, contrast changes, filtering, image mixing, etc., to existing images like shown on the right. Resampling methods also addresses dataset imbalance, either by creating or removing samples. Now, we discuss the following section on our experiments. We conducted a variety of experiments to obtain the best classification results. InceptionNet employs parallel convolutions of various filter sizes, 1x1, 3x3, 5x5, for simultaneous feature extraction, along with global average pooling at the output to reduce parameters and prevent overfitting. Synthetic minority oversampling technique (SMOT) was used to balance the training dataset by generating synthetic images for minority classes. An 80-20 split created training and validation sets. Image resizing, normalization, and a batch size of 64 were applied during model training for 10 epochs, with callbacks utilized. This model achieved a private score of 0.6098 and a public score of 0.6251. We utilized the Resny XT50_32x4D model, featuring a cardinality concept that enhances capacity and performance without significantly increasing computational cost. Its parallel pathways within each layer address model degradation in deeper networks, making it suitable for tasks like cassava leaf disease classification. Various pre-processing techniques, including resizing, normalization, and augmentation, were applied to improve model generalization and robustness. The dataset was split into 5 folds for cross-validation, with promising performance observed on validation data. Inference was conducted using weights from each fold, resulting in K sets of predictions. Final predictions were obtained by averaging across the K folds. This model achieved a private score of 0.8961 and a public score of 0.8980, demonstrating its effectiveness in accurately classifying cassava leaf diseases. Next, we selected the EfficientNet B4 model for its exceptional performance in transfer learning and computational efficiency. During pre-processing, we applied image transformations and augmentation techniques such as fmix and cutmix. Fmix blends transformations, while cutmix combines image parts for robustness. After training for 10 epochs, we saved the weights for inference. During inference, the test time augmentation technique was applied to the test dataset, with each image being predicted 3 times for improved accuracy. Final predictions were averaged across the 3 iterations. This model achieved a private score of 0.8933 and a public score of 0.8980, demonstrating its effectiveness in accurately classifying cassava leaf diseases. Vision Transformer is a transformer-based architecture designed for computer vision tasks, processing images as sequences of patches and using attention mechanisms to capture long-range dependencies between pixels. This global context understanding enables better classification of complex visual patterns. Image preprocessing techniques, including FMX and various transformations such as rotation and flipping, were applied to enhance model generalization and prevent overfitting. The dataset was split, and the model was trained for 10 epochs with and without early stopping, followed by predictions using the learned weights. This slide shows the hyperparameters used for training this vision transformer model. The presented slide displays the outcomes of the model based on the depicted factors. It is evident that the VIT-based Patch 16-384 model, combined with FMX augmentation in addition to other transformations and without early stopping, yielded a higher public score compared to other configurations. As ResNeXT and EfficientNet outperformed other models in our experiment, we decided to test an ensemble of these two. We used the saved weights from training the 2 models separately. Test time augmentation technique was applied to the test dataset, and the final predicted labels were aggregated using the weighted average method, where the predictions from the models are combined by assigning different weight combinations. We evaluated the ensemble on 2 dataset variations, with and without TTA, and received the following leaderboard scores. The ensemble performance has degraded with TTA, possibly due to overfitting on test data from noise. It is also notable that ResNeXT model performed worse with TTA, indicating sensitivity to it. Based on our experiment with transfer learning models for image classification tasks, the EfficientNet B4 and ResNeXT 50_32x4D models outperformed the others, achieving the highest scores on the public leaderboard at 0.8980. In conclusion, we gained valuable insights into image classification and machine learning workflows. We learned the importance of detailed exploratory data analysis and pre-processing, which laid the foundation for effective model development. Our experiments highlighted the effectiveness of techniques such as data augmentation, feature extraction, and transfer learning with architectures like EfficientNet and transformers in improving model performance. Furthermore, we observed the impact of starting with simpler methods before advancing to more advanced techniques like model ensembling and test time augmentation. Overall, this project emphasized the importance of continuous experimentation and refinement to achieve desirable results.